Hello, everyone, and a warm welcome to you all in attendance for the second installment of the IMechE Postgraduate Tribology webinar series. My name is David McMillan, and I'll be your chair for today's webinar. I am a subcommittee volunteer member of the IMechE Tribology group. I'm currently a third-year PhD student at the University of Central Lancashire. So these monthly webinars were created and put forward to provide a platform for early career tribologists and PhD students, master's students, postdocs to showcase their work, highlighting the diverse research activities throughout the UK tribology field across the many institutions from the top of the country down to the bottom. Today's seminar will follow a slightly different format compared to last month's, if any of you attended, and the normal format. There will be only one presenter as opposed to two, where we normally have two presentations, 15-minute talk with 5-minute Q&A. Hopefully our speaker will be able to give us a slightly extended talk of around 20 to 30 minutes, followed by a longer Q&A session. So I encourage you all to ask as many questions as possible and also submit these questions during the presentation as opposed to not all at the end. So without further ado, I'd like to formally introduce you to our speaker for today, Mr. Kian Kun Yap. Yap is a final year PhD student in the Tribology group of Imperial College London. Yap's work focuses on unraveling the development mechanisms of polymer transfer films using unconventional in situ techniques. Yap's presentation will explore the refractive index characteristics of polymer transfer films and their impact on film thickness measurements using using optical profilometry. The main goal of Yap's research is to provide a real-time thickness characterization of polymer transfer films during sliding tests to better understand their transfer mechanisms. So over to you, Yap, for your presentation.
Thank you, David, for the introduction. Can you see my slide and hear me fine?
Yep, we can see your slides and hear you perfectly fine.
So today I'm going to talk about the refractive index of polymer transfer film and why do we care. So before I proceed, I'd like to thank my co-authors, Mark and Janet from Imperial College, Sergey from EMPA, and Lucas from DuPont. So this is the most commonly used tribal pair in the industry, which is a lubricated metal-metal tribal pair. In some application, however, the use of liquid lubricants is not favorable. For example, in semiconductor or food industry, where the tolerance for contamination is strict, or in aerospace, where the lubricants fail due to vacuum. And without lubricants, machine can seize in no time. In this case, a polymer metal tribal pair is often used. This is because when we slide a polymer against a metal, some polymer will transfer to the metal counterface. And this is what we call a transfer film. And the transfer film often contributes to a low friction, making polymers a good material for self-lubrication. In my PhD, I use a pin-on-disc tribometer to study transfer films. In my case, the stationary pin was made of PTFE, while the rotating disc was made of 304 stainless steel. The tests were performed in a climate chamber where the humidity can be controlled, and two in situ techniques were used to observe real-time the development of these transfer films. The first technique is spatio-temporal mapping, which allows us to see how friction changes with wear track position and time. The second technique is high bandwidth microscopy that enables the tracking of the whole life cycle of transfer films. With the help of these techniques, we were able to achieve near ultra-low wear for neat PTFE, so without the use of fillers. I'm not going to go too much into detail, but if you're interested, you can always refer to our publication. The in situ techniques that I mentioned earlier are good. They help us to see what's happening during sliding, but they're not good enough. For example, if you look at this wear track video, it only tells us some 2D information, so only the shape and area of the films. This means thickness, height, and roughness information are actually missing. But if we can measure the surface profile real time, we can then quantify real time the instantaneous transfer or wear rates. This will give us more insights into the fundamentals of the system. In fact, technologies for measuring surface profiles in situ are nothing new. In general, I like to categorize them into three, which are inline, on wear track, and in contact measurements. With inline measurement, scanning profilometry is usually used, for example, confocal microscopy or LCSM. But measurement takes time with scanning method, so we need to interrupt the sliding test, send the disk to the microscope, usually using a motorized stage, take measurement, send the disk back, and resume the test. As we can see, this method is not real time, and there's disruption during the test. But the good thing is that the measurement is more precise compared to other techniques. For on-wear track measurement, non-scanning profilometry is used. For example, digital holographic microscopy or DHM. For non-scanning method, a single measurement can be acquired in microseconds. And because of this, we can put the microscope above the disk wear track and take measurement while the test is running. The good thing is that there's no disruption at all, but strictly speaking, this measurement is not real time. And I like to call it pseudo real time because the measurement is done outside of the contact, which means there's a slight delay in the measurement. To do real time measurement, we need in contact technique. For example, we can put a microscope underneath the disk and replace the disk with a transparent material, say glass or sapphire, so that we can see through the disk. This is common for EHD measurement, for example, and usually white light interferometry is used. The downside is that it is disruptive because changing the disk material can actually change the originally intended tribological behavior. Now, a little bit about how film thickness is measured using optical profilometry. If a film that we measure is opaque, thickness can be obtained from the optical path difference, which is caused by the height change between the substrate and the film surfaces. Things are more complicated if the film is transparent. This is because light can now go through the film. And because of this, the refractive index must be taken into consideration. And unfortunately, polymer transfer films are often transparent. If you look at this PTFE transfer film example, we can see the interference pattern, which suggests the transparency of the film. This means we need to know the refractive index of this film to quantify its thickness. Measuring the refractive index is challenging because polymer transfer films are often rough and discontinuous. And because of this, a common practice is to assume that the refractive index of the film is the same as the bulk polymer. We also assume this refractive index remains constant throughout the sliding test. These assumptions are probably fine for liquid films, like oil films, for example. But for polymer transfer films, they are ductile and can experience high degree of plastic deformation during sliding. This may change their refractive index. And worse still, many polymers are birefringent, meaning their refractive index in different directions can react differently to the principal stresses. Also, during a sliding test, there may be formation of new chemical products due to tribochemical reactions, degradation, oxidation, and so on. All this could contaminate the transfer films and affect their optical properties. So the question now is it okay for us to assume a constant bulk refractive index for a polymer transfer film? This is important because wrong refractive index will lead to thickness measurement errors. To find out, we carry out some pin-on-disc sliding tests to generate PTFE transfer films. And to study how refractive index changes with time, we also ran the test at different sliding cycles. So from 1 cycle up to 10,000 cycles. And here are the results. This is a graph of coefficient of friction and wear rate against sliding cycles. The left axis is wear rate, and the right axis is coefficient of friction. And as we can see, these lines overlap well with each other. This indicates a good repeatability of our test. Here are some typical transfer films from different sliding cycles. Most transfer films have similar manifestation, and they appear as small lumpy islands. The first sliding cycle is an exception. The films are much smaller, but anyway, all this agree with our previous findings. To characterize the thickness of these films, we randomly pick 35 films from each list and measure their surface profiles. All this was performed post-test and ex situ. 2 profilometers were used, which are confocal microscope or LCSM and digital holographic microscope or DHM. The confocal microscope represents a scanning profilometer, which is often used for inline measurement, while the DHM represents a non-scanning profilometer, which is for on-wear track measurement, usually. We quantified film thickness by first drawing a line profile passing through the highest point of the film, and then calculate the average height of the line profile. In this presentation, a measured profile means a raw profile measured without any surface treatment. And an actual profile means a profile measured after the film is gold coated for 10 minutes. The respective line profiles are shown in the right graph here. And as we can see, thickness of the measured profile is estimated compared to the actual profile. We know what we measured after the gold coating is the actual profile because we have verified it with the AFM measurement. The orange and red lines are profiles measured by AFM. And as we can see, compared to the both the AFM measurement and the actual profile, they match well with each other. And why do we code it for 10 minutes? Why not 1 minute or 20 minutes? So this graph is the line profiles for different coding time. The thickness increases as the time increases. And as we can see, film needs 10 minutes of coding time to become fully opaque. And that's why you see a stabilized profile. And that's why we choose 10 minutes. And also, imagine if you're measuring a transfer film without coating or not having enough coating, we can see that from this graph that we actually are not getting the actual profile. And in fact, this is a mistake I often come across in some publication. So far, we have talked about a lot about thickness measurement. How about refractive index? So how do we characterize refractive index? We first work out the governing equations for both confocal and DHM measurements. This equation relates the refractive index and film to the measured thickness Z and the actual thickness T. For DHM, we use phase shift instead of Z. but they are both the same thing. We can then solve the refractive index by adjusting the measured profile until it matches the actual profile. The profiles are considered matched when the areas under the graph for both profiles are equal. Here are some examples of measured profiles using confocal. Blue lines represent actual profiles and orange lines present measured profiles. The left graph is a typical profile with a good match, while the right graph is a typical profile with a bad match. And as we can see, some profiles match better than others. If we simplify and rearrange the governing equation, we can see that there are only two independent variables in the equation, which are the refractive index, N film, and the measured thickness C. This suggests that any mismatch between the measured and actual profiles is either caused by C due to the noise in measurement or N film due to the change in refractive index. The same goes to DHM measurements. Mismatch is either caused by phi due to the noise in measurement or N film due to the change in refractive index. And in the equation, lambda is simply the laser wavelength, which is a constant. To check the influence of noise, we have three line profiles here from repeated confocal measurements on the same transfer film. Since we are measuring the same film, any influence from the change of refractive index is eliminated. And as we can see, the repeats match perfectly with each other. This means that the effect of noise is insignificant. And same observation for the DHM measurements. And this confirms that any profile mismatch is caused by the change in refractive index instead of the noise in measurement. Now, to quantify how good the measured profiles match the actual profile, we plot the measured profile against the actual profile and calculate the correlation coefficient R. And if the two profiles have a perfect match, we should see all data points line perfectly along the fitted straight line. And R should be equal to 1 in this case. And this also indicates that the refractive index within the film is homogeneous. However, if the two profiles have a poor match, we should see data points scattered along the fitted line. And R should be closer to 0 this time. In this case, the film is inhomogeneous internally. This is a graph of refractive index against correlation coefficient R for confocal measurements. And this is the same graph, but for DHM. The red line represents the average refractive index for the confocal measurement, which is 1.66. The green line is the average refractive index for DHM, which is 1.43. And the black line here is the refractive index for the bulk polymers, which is 1.35. We can see that both confocal and DHM give a higher refractive index than the bulk polymers. This suggests that the average refractive index of the transfer film has increased compared to the bulk polymer. We also see that the confocal gives a higher refractive index than the DHM. And I'll talk about this later. Besides that, we can see the data points scattered across the x-axis, indicating that different transfer film have different correlation coefficient. This suggests the inhomogeneity of refractive index within a film. And also some films are more inhomogeneous than others. We also see scattering of data points across the y-axis. This indicates the inhomogeneity of refractive index between the transfer films, meaning film A may have a different refractive index from film B. So far, we have seen how much the refractive index of transfer films is different from the bulk, and also the inhomogeneity of refractive index both within and between transfer films. So the question now is what causes these changes? So we'll first start with the effect of sliding cycles. So on the left, we have a graph of refractive index against sliding cycles for the confocal. And on the right, we have the same graph for DHM. And as we can see, the fluctuation of refractive index in the first cycle is much higher compared to all other cycles. And as mentioned earlier, this is simply because the films in the first cycle is so much different from the rest. But if we exclude data from the first cycle, we actually see no obvious changes in refractive index with the sliding cycle. The second effect we'll look into is the effect of stress. So what you're seeing is a photoelastic image of a typical transfer film. The color represents the residual stress in the film, and the color variation indicates the stress inhomogeneity within the films. We see this color variation because there's a change in refractive index due to the change in stress. In other words, the stress inhomogeneity also implies the inhomogeneity in the refractive index. This seems to agree with the internal inhomogeneity we observed just now. However, for now, we are still not sure how much of the changes in refractive index is actually contributed by the stress. And we also look into the infrared dichroism of transfer films using polarized FTIR. So it tells us information about the chain orientation of the films. This is a typical IR spectrum for PTFE. In this study, we use asymmetric stretching mode of the CF2 bond in PTFE. The vector of the dipole moment for this vibration mode is perpendicular to the chain orientation. So when the polymer chain is parallel to the sliding direction, a 0-degree polarization will get a high IR signal, and a 90-degree polarization will get a low IR signal, and vice versa when the polymer chain is perpendicular to the sliding direction. The dichroic ratio is the ratio of 0 to 90-degree polarization. So long story short, the more oriented the polymer chain to the sliding direction, the higher the dichroic ratio. At the same time, this also implies that films are stretched more in the sliding direction. This is a graph of dichroic ratio against film thickness. First of all, most of the data points here have dichroic ratio greater than 1. This means most films are stretched and oriented in the sliding direction. And we can clearly see a negative correlation here. In other words, the thinner the films, the more oriented they are in the sliding direction. This makes sense because thin films are easier to be stretched, and at the same time, stretched film will also get thinner. And this is a graph of refractive index against tensile stress for PTFE films. And by the way, this is not my work, but I borrowed this graph from a paper. And as we can see, when a film is stretched, we expect a decrease in refractive index, and vice versa when a film is stretched. Our findings actually contradict with the literature because we saw an increase in refractive index in the transfer film. And at the same time, we found that most films are stretched or in tension. But if they are in tension, the refractive index should then have decreased instead of increased. Here we plotted the dichroic ratio against refractive index. and we see no obvious correlation between the two parameters. This suggests that the tension in the films is either too small, cause a decrease in refractive index, or maybe the decrease is cancelled by the compression due to the normal load or other factors which can actually increase the refractive index. Okay, just now we saw the confocal gives a much higher refractive index than the DHM, even though the same set of transfer films were measured. For your information, the confocal used a laser with wavelength of 400 nanometer, while the DHM used a much longer wavelength of 2800 nanometer. And in fact, refractive index is also a function of wavelength. This graph shows how refractive index of a PTFE film changes with wavelength. The left end of the line represents the wavelength of confocal, while the right end represents DHM. So obviously, we should expect a decrease in refractive index as we increase the wavelength. However, this change in refractive index is less than 0.02. Less than 0.02, yes, and which is much smaller than the change of 0.23 that we measured, which is like 10 times larger. So what causes this big difference? This graph here shows how refractive index changes with wavelength as we add iron oxide in a glass sample. Again, this is not my work, but I get this from a paper. And from this graph, we can make two observations. First, we see an overall increase in refractive index as more iron oxide is added. Second, the increase is more significant at lower wavelength. This is because iron oxide is brown, so it reflects red and green lights but absorbs blue light. And due to the absorption of blue lights, the increase in refractive index at lower wavelength is higher. If you remember, we see a very similar trend in our measurement previously. So it makes sense for us to suspect that there's contamination in our transfer films, which causes the increase in refractive index. So from our previous study, we know that the tribochemical reaction between PTFE and steel will form brown substances. If we look at this image here, we can see evidence of these tribochemical products in the transfer film. And these products were picked up from the wear track during sliding. And it is very likely that this changes the refractive index or increase the refractive index of the films. The last effect we'll study is film thickness. These two graphs are showing refractive index against film thickness for confocal and DHM respectively. And as we can see, fluctuation of refractive index decreases as thickness increases. Well, what does this mean? Imagine when we are measuring the thickness of a transfer film, and because we do not know the exact refractive index for each film, we'll have to make an assumption for the refractive index. Say if we use the average refractive index that we have measured earlier. So for confocal, this is 1.66. So any transfer films that have a refractive index deviates from the mean will cause a thickness measurement error. In other words, the larger the deviation of refractive index from its mean, the larger the thickness error. Here we convert the refractive index deviation to thickness percent error. One thing we can observe is that thickness error decreases with the increase of thickness. This means that we are more confident with measuring a thick film than a thin film. Here I added two lines in each graph to show the range of thickness error for the film population. I'm using a 4 sigma here, which means 95% of the population will lie within this range statistically. And as we can see, thickness error for confocal is around plus minus 10%, while DHM is much larger, which is about plus minus 40%. This means that the change in refractive index is actually significant and can lead to a big thickness measurement errors. A remaining question now is why the error from DHM is larger than the confocal. Here I have the governing equations for confocal, DHM, and white light interferometry. And I convert this equation into thickness percent error. And this graph visualizes the three equations that I showed you just now. And it tells us how thickness error changes with refractive index for different optical techniques. And as we can see, both confocal and DHM are sensitive to the change in refractive index, with DHM showing a higher sensitivity than confocal. And the sensitivity of white light is independent of the change in refractive index. And with the plotted within the plotted range, white light has the lowest error compared to other techniques. So from this graph, we can see that different optical techniques have different sensitivity in terms of error. And to sum up, we have seen a significant change in refractive index for PTFE transfer films. And this change can lead to a significant thickness error. And if we assume a constant refractive index for all transfer films. So for post-test or ex situ measurement, we can still prevent the error by coating the films or using mechanical profilometry like AFM instead of using optical techniques. And if it is an in situ measurement, we need to understand how much error to expect and our tolerance for the application. And at the moment, we're still working on building a predictive model to estimate refractive index. So hopefully one day we will be able to make accurate in situ thickness measure for polymer transfer film. Thank you.
Thank you very much, Yap. So we're going to have a few questions. I actually have one for you. So why did you choose PTFE for your research and not other polymers, maybe PEEK?
We chose PTFE for two reasons. So one is because PTFE is one of the most commonly used high performance polymers in engineering applications. And second is because PTFE is well studied. So for this kind of study, it's good to first start with something that we know. That's why, yeah, we chose PTFE.
Okay, thank you. I've got another question as well. You know, you was using a pin on disc. Is there a possibility to look at other contact geometries? Maybe a ball on disc.
For what application?
For looking at the for the polymer transfer films.
Yeah, that's possible. Yeah, that's possible.
Yeah. Okay, thank you. And these are quite seem invasive methods. Do you think any of these methods could possibly be used like outside of the laboratory, like in a real world application? And if so, would there be any potential benefits, any applications which would benefit from doing that?
I would say as we know, there are always a limitation with institute techniques. And for these techniques that we are using, I have to say that they are limited to lab use.
Yeah.
So
Yeah.
only for this tribometer,
Mm-hmm.
because it's very difficult to use these optical in situ techniques for real application. I would say for real industrial application, we'll usually choose some non-optical technique like ultrasonic or
Yeah.
maybe eddy current.
Yeah. So is that a case of it being so difficult to implement and the cost to implement it?
I think it's about the usually in real industry applications, you need access to the contact,
Yes.
etc. But with optical technique, it's very difficult to get the optic access.
Okay. I have another question as well. So the PTFE falls under the category of PFAS, aka the forever chemicals. How would the potential ban on these PFAs in the EU affect your research?
That's very good question. So as we know, the EU is planning on banning PFAS, and how would ban of PTFE, the potential ban of PTFE in the future affect by research? So that's your question, right? I think say even if the PTFE will be banned in the future, it's still useful for us to study the fundamental of PTFE,
Mm-hmm.
so that in the future we can use what we have learned from PTFE as a reference for us to formulate new materials, which is like PFAS-free materials, which we can use to replace PTFE.
So can
And
you?
as we know, yeah.
Sorry, can you apply this to other transfer films? Maybe not polymer.
You mean applying the in situ techniques that we use to other polymers?
Yes.
Yeah, that's possible.
Okay. Okay. Well, I would like to say thank you very much, Yap, for coming and doing this very insightful talk, and thank you for extending your talk on such short notice. So that concludes the question for you, Yap. So that wraps up this month's IMechE Tribology webinar. Hope you all who has attended enjoyed the presentation as much as I did. I really enjoyed that. Thank you very much. It's a great showcase of the postgraduate research happening across the UK, and specifically today, the Tribology group at Imperial College London. Thanks again, Mr. Kian Kunyap. There will be no webinar in December because we have the IMechE 30-second mission of Tribology, which is at IMechE HQ on the 6th of December, the mission. There will be more oral presentations and poster presentations from postgraduate students, and there'll be a chance for networking. So try and get down if you can to the mission. This year, the talks for the mission will be in the main hall, with refreshments will be available, all free of charge for the free to attend event. The final submissions for the oral presentations have actually already elapsed. There will be 9 presentations for the mission, starting at 12 noon and finishing, I believe, at 4:45 on the 6th, and then followed by the Donald Julius Groham Prize Lecture in the evening. But there is still chance to submit a poster abstract for the postgraduates, and I would strongly encourage this because there are industrial sponsors this year at the event. So I believe the first prize for the post presentation is £200. So definitely try and submit an abstract for the poster and bring it on down, bring yourself down. The information to submit the poster abstract is on the IMechE Tribology group webpage on the Mission of Tribology window at the right-hand side. So the next IMechE Tribology webinar will be in the new year, commencing in January, and then every month from then on. The speakers in January will be Rui Dar of the University of Sheffield, I believe, who's just obtained PhD in February, and Amira Masood Kia-Kajori of the University of Southampton. Their talks will focus on rolling contact fatigue in wind turbine gearboxes and machine learning algorithms for intelligent fault detection in rotor systems. So hopefully you can attend those webinars in the new year. So once again, I'd like to extend a big thanks to Mr. Kian Kun Yap for your talk. Very, very interesting talk, I must say, and all of you for attending. And I look forward to hopefully seeing some of you in person at the mission on the 6th. And if not, please try to come back to these webinars in the new year to see the showcase of diverse research happening across the UK. So thank you, everyone, again, and hopefully see you all soon. Goodbye.